We now present a lecture by Dr. Ben Roberts, delivered in January 2025, on the topic of innovative housing design to keep cool in the tropics. Dr. Ben Roberts is a lecturer in building energy at Loughborough University, specialising in thermal comfort, indoor air quality, and health in buildings. He completed his PhD through the London-Loughborough Centre for Doctoral Training in Energy Demand, the ERBE CDT's predecessor, researching overheating mitigation in UK homes. Ben's work spans extreme heat in informal settlements, air quality in hospitals and mass gathering venues, and building performance measurement and modelling. He has led international field trials, coordinated model validation studies, and won the CIBSE Carter Bronze Medal in 2020. The ERBE Seminar series provides a platform for discussion and dissemination through themed events sharing innovative ideas and research in building energy performance. The series is co-organised by the CIBSE Young Energy Performance Group and the ERBE Centre for Doctoral Training to promote critical discussion and collaboration. The fifth seminar event included 4 presentations surrounding a new eco-village in Tanzania. These included the design of the school for thermal comfort, empirical research on natural ventilation, mechanical cooling and dehumidification strategy, and a dialogue on the construction process. Please do support the series and attend a future event, either online or in person. And without further ado, Ben's lecture will begin.
Thank you all for coming, and thank you to everyone for coming online. Thanks to Tom for organising this session. So I'm going to talk in 15 minutes, not 25, about innovative housing design, keep cool in the tropics. I've just come back from 2 weeks in Ghana, so this is hot off the press data to share with you all today. So the aim of the project was to co-develop low-cost interventions for retrofitting informal dwellings in culturally sensitive ways to reduce heat stress and improve well-being. Just to say, I'm standing at the front here, but there's a big team involved both in the UK and Ghana. So this was the REFIT project, reducing impacts of extreme heat to improve well-being in cities, led by Professor Kate Goff at Loughborough University, recently moved to Lund University in Sweden. And then we had half the team were from Ghana and the other half of the team were from the UK, and I was the researcher on the project. Also, a big thank you to our advisory board. We worked with people who are in charge of the Ghana Health Service, Ghanaian building regulations. We had people from government, industry, architects. So these are really important to the way we adapted our culturally sensitive, appropriate retrofits. I probably don't need to tell you this, but the climate is warming. This is 1965, 2004, 2024. We're having massive amount of surface warming, which is going to hit tropical Africa particularly hard. So temperatures are going to increase in tropical Africa more rapidly than elsewhere in the world. My work is centered on Ghana. That's a country in West Africa. We work in 2 cities, Accra in the south, Tamale in the north. 25% of the population of Ghana is poor, so not everyone has access to air conditioning. Not everyone has access to the means to make expensive retrofits to their homes. So a lot of the work we did was around making sure retrofits were also affordable. But really, Ghana is on the front line of climate change. Rapidly warming climate, high level of poverty in the population, inability to retrofit if you're in the poor community, unstable electricity supply in many communities, so air conditioning isn't necessarily an option. Our work centered around these informal settlements. These are places where people don't own the land. The government owns the land, but at any point the government can come in and reclaim that land. So people here don't want to spend a lot of money on their dwellings, on their houses. They don't want to make big investments, but they're also the people who can't afford air conditioning, can't access air conditioning in very densely occupied spaces with not much fresh air, not much ventilation, exposed to the urban heat island. We did a lot of monitoring work. We measured temperatures in 131 houses. We found some really high temperatures, 50 degrees, 38 degrees in hospital. So these are like really uncomfortable, dangerous temperatures in these environments. We found also that roof type was a key modifier of indoor temperature. So what we have here is time and temperature. In a house with a thatched roof, we got quite a stable temperature, which meant it was hotter than outside during the night, but cooler than outside during the day. Metal roofs were the complete reverse, hotter during the day, but cooler during the night. So we know that building design can modify the indoor environment. And this was something that I found really interesting. If you've ever played with an IR camera, you always hold it up and your hand glows white. Well, we went into this house, it was a metal roof, and our hand was the cold thing in the room. The metal roof was 50 degrees. So that was just like, that just summed it up for me that, you know, we're dealing with some extreme heat here. So although thatched roofs are good at keeping temperatures low during the day, they're not a culturally acceptable thing to use anymore for building materials, in this part of Ghana, at least, we were told. So we had these 3 research questions. How do people perceive indoor temperatures? What building adaptations could we use to reduce temperatures? And then how effective might these adaptations be at reducing temperatures? We did a number of things. We did thermal comfort surveys. We asked people how they felt in different environments. We used worn sensor diaries of people were wearing temperature sensors on their wrists or around their necks and going around and telling us where they were and when. We were looking at the types of temperatures they were experiencing. We did photo voice surveys where people were taking photos of areas where they felt hot or cold, types of buildings they liked, types of buildings they didn't like, and then we did interviews. And this was mainly where we picked up the fact that thatched roofs aren't modern. We need to move away from thatched roofs. People don't want to build in that way anymore. And then we also did some building simulations and experimental buildings, and that's what I'm going to be talking about today. So everything we've done has been backed up by lots of interviews, speaking to people, making sure what we're doing is culturally acceptable, affordable, accessible, and available. So here's our 4 experimental buildings. We built 4 identical buildings to test different things like ventilation, shading on the indoor temperature. So I don't know if you've ever heard of the NASA twins. So there's a pair of twins. One got sent up to space, one got left down on Earth. They did lots of things. They then brought them back together. They'd been exposed to different environments. They were able to compare their physiological responses. It's a twin study. We did exactly the same thing here. We've got our twins, all our houses, which are identical. If you change the ventilation in one or the other, you can compare the temperatures across to isolate the effect of different ventilation interventions. It's quite a simple but powerful method. Before we built our test houses, we did some building simulations. We used computer models. Obviously, it's a complete waste of time and money to go ahead and build 4 houses which actually aren't testing the right things. But we built 49 different model variants to test different types of material, ventilation, shading. And what this showed was the best thing you could do. The coolest house was one with a ventilated roof structure, remarkably like Andy's design, with an overhang insulated ceiling. The worst thing you can do, the hottest thing, was going to be a house with a wooden wall, low thermal mass, heats up really rapidly, you get high peak temperatures. Thatched roofs, yeah, pretty good, but we know people don't like them. We know there's issues with dust and pests and fire. So this kind of guided the ventilation systems that we trialed in our real buildings. Of course, this is all based on computer simulations. I've done some other research which showed that the computer simulations are quite uncertain. The results you get out of it aren't necessarily what you see in reality. So it's really important that we went on to build these 4 houses. We built it out of sandcrete. So sandcrete are these blocks you can see here. They're basically loads of sand, a little bit of cement, all mixed up with a bit of water, put into a metal mold, tipped out. And that's what most people in this part of Ghana were building their houses out of. We asked people, if you were going to build a new house, what would you use? They told us sandcrete. They said, I'm going to use a metal roof and sandcrete walls. So that was basically our base case design for our experimental buildings. We also were very realistic. We put mosquito mesh on the windows, even though no one was going to be living in these houses. And we measured the indoor temperature at all different heights, looking at temperature stratification. We measured the weather. And then we were able to answer this research question 3, how effective are these building materials or adaptations at reducing indoor temperature? This was one of the things we thought of as our main innovation, was this sort of ventilated roof structure. Now, there was a bit of a miscommunication between us, the architects here, and the builders. It wasn't meant to be this big, but I'll talk about that in a minute. And there's another example. So basically 3 identical houses. This is identical, except it's got a big open area for air to move up and out, hopefully provide cooling. We'll see. So we did 11 different tests, so basically 11 different combinations of ventilation in all the different houses, 303 days worth of data for us to analyze. This is what we found. Okay, how am I doing for time, Tom?
5 minutes.
5 minutes to go.
Just 7.
7, perfect. I've gained 2 minutes. Right, okay. So we've got time along the bottom. We've got temperature difference on the sides. This isn't actual real temperature. It wasn't -3 outside. This is the temperature difference from house 2, house 3, house 4, compared to house 1, which is the base case. So house 1, no ceiling, windows always closed, all the way through all the tests. So remember, house 1, no ceiling, windows always closed. Then in house 2 and 3, we open the windows. In house 4, we open the windows and use this big ridge vent. And I think it's quite obvious what's happening. The one with the ridge vent and the windows open at night is almost 2 degrees and sometimes more than 2 degrees cooler than the house without any windows open. And it's much cooler than the house with windows open. So you open your windows, you get about ½ degree temperature reduction at night. You add this ridge vent as well, you get a much greater temperature reduction. So this stacked ventilation, the movement of hot air up, out through the building, being replaced by cool air from the outside, is making a statistically significant cooling effect of 1.4 degrees during sleeping hours. So that's great. That's a significant reduction in temperature. I think that's something worthwhile doing. The issue was, and actually this brought it down to 25.1 degrees inside on average. So in the UK, we say if the temperature is above 26 degrees, sleep starts getting disrupted. So someone might be able to sleep more comfortably in the house with the ridge vent. That's pretty good. What happens if we close the windows? So if you close the windows in all the houses, it just completely removes the effect of that ridge vent. So the ridge vent doesn't work unless you've got windows open in combination. And that's because it's shutting off that stack effect. Obviously, the air's moving out. It needs to be replaced by air from somewhere else. Otherwise, we create a vacuum. So ridge vent is only effective in combination with a window in this example. People told us they want to have a ceiling in their houses because it stops birds and bats and mosquitoes and things coming in through your roof into your house. So people want a ceiling. This is what happened when we put a ceiling in the house. So house 1, no ceiling. House 2, ceiling, windows open. House 3, ceiling, windows open. House 4, ceiling, windows open, and a ridge vent. What is good to see is that even with the ceiling installed, you think that might cut off the ventilation, you still get a temperature reduction at night in the house with the ridge vent. So what's happening is the windows and the ridge vent are still providing enough ventilation to bring the temperature down at night by almost 1 degree centigrade. The interesting thing we found was actually with the ceiling, the temperature was slightly warmer than one without the ceiling in the day. And that contrasts what I showed you right at the start of the lecture from our measured data from our field trial. We were quite surprised by this, but the ceiling we installed was really thin, had no insulation. So maybe if we put insulation in the ceiling, we might also be able to reduce these daytime peaks. Okay, last one to show you is that if you are or not opening a window. So the windows were open in house 3 and house 4. They were closed in house 2. There's a ceiling installed in all the houses apart from house 1. What's quite interesting to see is that this blue line, there's a ceiling but no windows open. So you get a little bit of protection during the day, but at night, because you're not either ventilating via the windows and ridge vent or losing heat via the uninsulated ceiling, you get an increase in temperature difference at night up to about 1 degree. So basically, if you're going to put a ceiling in, you must ventilate, otherwise you're going to have a problem at night. So basically what I'm trying to say is that ventilation is really important. And of all the things we tried lots of different ventilation, insulation scenarios, which I haven't had time to go into. Of all the things that we tried, the only statistically significant effects were from window opening or ridge vent opening. Nothing else was effective, which was quite disappointing in some ways, but also it's kind of what we expected. So really, in summary, ventilation is important. In fact, ventilation is vital for cooling these types of dwellings. It makes roof vents more effective. It counteracts the warming effect of ceilings, but they must be used at the right times. You must open your windows at the right times because it can make it warmer during the day when it's hotter outside than in. So we need to be careful. Ventilation is important. The problem is this. People are covering their windows. They're covering their windows because of dust ingress. They have a big dust storms. Dust comes down from the Sahara with the Hamatan winds, coats everywhere in dust. People want to close their windows. The sign of modernity is moving away from louver windows and towards these sliding windows, which don't have such a large available open area. So I've just shown you how important ventilation is, but people are actually restricting the ventilation they have available in their homes. We did a lot of work also with the communities. We showed them our designs. We told them this is effective at reducing their temperatures, but people said, well, unfortunately, we don't like it because it looks like a house for bats. So this thing here is where all the bats are going to roost at night. So we said, okay, we went back to the drawing board. We modified the roof and we put this little gable vent in to try and increase the ventilation. Those kind of tests haven't been analysed yet, but you can see that sometimes, even if you're showing a community, this is going to reduce the temperature, if it causes other problems like bats, it's not going to be accepted. But we also designed this chimney thing to, again, we got feedback saying the ridge vent's going to let mosquitoes in. So we tried this chimney, which has got mosquito mesh around the top, and you can open and close it, again, to try and allow ventilation out of the occupied space without letting bats and mosquitoes and dust and stuff in. So we've got a few more tests to analyse. The smaller ridge vent, the gable vent, the chimney. We're not concerned with occupant behaviour in these houses. We're not concerned with roof colour or vegetation. I can see Tom's ready, so I'm not going to tell you why. Happy to answer that in the Q&A. But thank you very much for listening.